So you will recall that we're talking about fluid dynamics. Specifically, we're talking about Bernoulli's equation and talking about how we can use that in some useful ways. So let's just, as is our protocol, let's talk about some of these things. I didn't want that, but that'll come later. We talked about Pitot tubes. And so the tragedy of, I guess, 4 or 5 years ago, in summer of 2009, there was an Air France flight leaving Rio to Paris, and lost contact with control. Never arrived. The unfortunate thing they always do is that they calculate how long it can be in the air before it arrives in Paris, and then after that time they start announcing what's going on. In that particular case, there was no information as to what happened to it; just disappeared. And it had disappeared as it went off the east coast of South America. An Airbus 330, which is kind of like a 777. And apparently it flew through, after the fact, it became apparent that it flew through a thunderstorm. And when the black boxes were ultimately recovered, probably a year or two later, in very deep water off the east coast of South America, east coast of Brazil, it went through some random moves, gaining altitude, losing altitude, and it turned out that the reason for the problem was that the Pitot tubes had potentially iced up in the very cold atmosphere inside the thunderstorm which it flew through. And so, surprisingly enough, as you mentioned a couple of times, for all the sophistication that we have with GPS and the technology that goes around non-destructive testing of planes to make sure they don't fall apart in the sky due to fatigue loading, like we saw for the Comet now, and that as fleets get older and older, we test them continually to make sure that they stay airworthy and go beyond their service life and can be restored to carry on much past their original design service life, that the most rudimentary of instruments that's been around for a couple of hundred years, a Pitot tube, is used to be able to define airspeed. And you'll typically see these on any plane. I guess I was going to say it's right there, but I guess you don't have to say that. It's identified for you. It's just a front-facing tube which has an open portion at the very tip. If we can still see it here. So this tip is open, and it goes down here to a pressure transducer which measures the pressure. And it will also have a double cylinder. It will also have an opening on this side here, which also registers to a different pressure transducer. And by measuring the differences in those pressures, you can say something about the airspeed from the calculations that we did before. Relatively straightforward. And so the geometry of this is very, very simple. This is how it physically looks. It's a tip here that has the velocity impinging on it, and so that the velocity that was some magnitude ahead of the plane, relative velocity, okay, so it's the plane that's moving and it's the air that's static, but you could also think of it as being in a wind tunnel where the plane is static and the air is moving past it. It's probably an easier conceptual way to think about it. So if this is coming at some velocity relative to the Pitot tube, it stops here at 0, and you can measure the pressure at this location 3. Likewise, the air flowing past it, it doesn't have to stop, and so it's just moving at the same velocity as it is here, and so the pressure on here won't be changed in the same way that this pressure is changed by saltation, what we call saltation, arresting it. And so this pressure, point 1, would be the natural pressure way in front of the plane, atmospheric pressure. And so what you can do is you can write Bernoulli's equation. Hello? Oh, we have 2 people. Great. You can write it at 2 locations. You can write it at this point 3, which represents this pressure at this point. We can write it at point 2, which represents this other pressure. I guess we can write it on, this is one streamline, so we can write Bernoulli's equation on there. We can write it along another streamline, which would be the green. I guess I should have done 4 on this side. Same. So we can write them at these 2 different locations, and then we can combine them because 4 and 1 should actually equal the real pressure. and we can apply that pressure to be able to substitute into here. And as a function of that, we have the velocities defined, once we take the square root of this, as a function of the difference in the two fluid pressures, the difference between the static pressure at this point, 4, and the pressure in the frozen tube, if you like. And so if we can measure 3 and 4, we can get the velocity, is the short answer. And so it's interesting that it's such a simple instrument, but it's relatively reliable. In the case of the Air France flight, the lack of reliability was a problem that I think other Airbuses had, and that was that they froze. And so clearly if you get moisture in here and either one of these ports freezes with a droplet of water on it, then you can't measure any pressure in here until it's reliable. And I think that was what was happening. So the solution to that is to have heated pitot tubes. So they heat them they heat them warm enough so that it melts the ice that forms. And so it's just a way of being able to define from arresting the flow at this point here, making the velocity 0, you can find out exactly what the unknown flow velocity, some location ahead of you, is. And of course it's the relative flow velocity to the plane speed versus the airspeed that's of importance, the so-called airspeed, I guess. And it doesn't matter whether the plane is static and the air is moving, or the vice versa of that. Okay? And so, very straightforward idea. You could imagine some wrinkles on that if the Pitot tube wasn't quite perfect. And so in these points here, this little hole in the side of the tube that feeds into this second green annulus, so it's a tube inside a tube, that's why the green is on both sides. If you don't have this perfectly made so it's nice and flush, you won't necessarily measure only the actual air pressure, ambient air pressure around you. And so you'd like it to look exactly like this, so that the fluid going across the top doesn't get decelerated by hitting a lip or going over a lip. And in this case, you'd expect that the pressure that you measure would be the real air pressure at that point, which you're saying is also the same pressure as the pressure 100 meters in front of you, where the air velocity is whatever it is relative to the plane. If you happen to misdesign it so that you had a lip on it on the downstream side or the upstream side, then you can imagine from what we know about Bernoulli what would happen to that. If it's on the downstream side, you could imagine that a portion of the velocity here, instead of going nicely over the top, would be 0. And if it's 0, then you get a portion of pressure head contributed, which would be detracting from the, you get a pressure developed by killing this. So if you change velocity squared, I guess it has to be the bracketed term, you'd get a change in pressure that results from that. And so you get a spurious pressure which you don't want. So you probably don't want this. And the other thing you probably don't want is, you can imagine that if you had a lip on the other side, then this all of a sudden is actually a bit like this. And we talked last time about the pressure distributions we have in a fluid. You know, if we drew the pressure distribution from the top in the fluid, we know that the fluid pressure in a liquid would be rho g h, I guess we should call it, is the pressure distribution. That's P, not rho. And we know that if it's going over this bump, then the pressure distribution would be reduced by some amount. It's reduced by some amount really because we're getting acceleration over the top, which is changing the value of g. And so that would also make some difference to this. And you could imagine that in that particular case, the pressure that you'd measure here would be less than the real pressure. And you don't want that either. So that's Pitot tubes. Interesting enough that we use those. Apparently you can have direction finding Pitot tubes. You can imagine that if you had Pitot tubes that were looking in maybe 3 different directions, you could look to see where the velocity was killed off the most and the pressures due to that were highest, and that would be the direction in which the flow was coming, right? So if this had the highest registered pressure in it, it would be killing the largest velocity, and so you could imagine triangulating the wind direction based on this static array. So you have a static array, you know where it is, you know its orientation, you look to see what the pressure changes are in each of these, you find the one with the highest one in it, and the direction of flow would be closest to that one. And that kind of makes sense as well. Hopefully it makes sense. So yeah, so it's always interesting, I think, that pitot tubes are related to such a simple instrument which is used to be able to do such important things on so many flights every day. And I don't quite know why. I presume that GPS isn't quite as accurate enough to be able to get the velocities, or perhaps it's a fail-safe mechanism to do it in case it goes out. I'm not quite sure, but nonetheless, it's the case. Okay? All right, let's do something with our knowledge of Bernoulli. So let's take a look at this again. Hope you're not getting... So we have enough information now to be able to do something useful with our understanding of fluid mechanics. And so if you're designing something like this, the so-called jet lev, 128,000 I think it was, I listened to the tape again last time, so not inconsequentially inexpensive. So if you're designing this, then you could imagine that you'd want to be able to figure out whether it's feasible based on what kind of plant you'd need in this umbilical cord that attaches to the power plant, which is towed behind it. You can see this kind of Thule ski rack type coffin thing that's being carried around it, pulled around behind it. And presumably that has some self-contained engine in it, motor in it, which has a compressor, which compresses the fluid and then puts it up this yellow umbilical. And then from this yellow umbilical, it gets directed to be able to lift this off the ground using some kind of throttle, I suppose, to turn up the power in the pump and to increase the flow rate as a result of that. And so the question is, do we have enough information now to be able to do some things to answer some questions? So typical questions I could imagine might be to be able to say something about what kind of flow velocity do you need to be able to get yourself off the ground. We saw the Jackass video as well, and so that's the same thing but with a fire hose. And the other thing might be, if you're going to have a pump to provide that, what would be the rating of the pump that you might need to do that? And so, do we have enough to be able to say something about that? I think we do. And so let's kind of think about that ourselves. I know you do. So I can be more definitive than that. Okay. So let's think about exactly what we might want to know. Where are we? Is it 5? Yeah, it is 5-1. I was thinking it's 6-1. Yes, thank you. Oh, I feel that it's going to be a good writing day today. It looks fantastic. So we're still Bernoulli, right? Our good friend Daniel. Okay, let's see if I can draw our guy. So let's mess around with this for a while. So this is the thing that's on the guy's back, guy in this particular case. And it has a jet of water that's coming out of it. And we have this guy who will go non-gender specific. We'll have him as a person, the weight of the person sitting on this thing. And we have this impinging on the water, which we'll just take as a straight surface. And so you can imagine that we have a flow occurring in here, and it's at some velocity. And so let's just go through this, and I'm going to take 4 locations. I'm going to take location 1. I'm going to take location 2. I'm going to take location 3. And where it hits this, I'm going to take location 4. And so from Bernoulli, we know that we have these components: elevation head, pressure head, and velocity head. Now I'm going to make a table out of these. And so these are the things that we know. So we've always said that we need to write it along a streamline. So a streamline would be something that joins all of these 4 things together. So they are all on a streamline. And so you need to be able to think about what we would know about this system. What do we know about this system? Well, as we have water going into this jetpack, we know the elevation, so I'm just going to do tick marks. The pressure, well, that's a bit problematic. We presume that it kind of be a high pressure, right, because it's squirting out. So I don't think we know what that is, but it would probably be kind of high. And it also has to be going at some velocity. And again, we don't really know what that is, but it's probably also relatively high as well, because perhaps it's not high. I get that everything is relative. But certainly the pressures are going to be high compared to other places. So this is point 1. Point 2, it comes out of this. What have we said about that? Pressure acting horizontally at point 2 on the jet as it comes out has to be atmospheric. Pressures acting at point have to be the same in all direction. So I think this should be atmospheric, which will take us 0. Oh, sorry, wrong one. We know the elevation, and this pressure should be 0. And we don't know what this is, but maybe this is what we would like to find out. We said there's 2 things we might like to find out. The velocity which is going on, to see if we get high enough velocity from our pump to be able to lift us up. And maybe also figure out what the rating of the pump might be to do that. Point 3, elevation. Well, we certainly know that if we choose some dimensions here. Pressure, same argument as before. Horizontal pressure is atmospheric, and so this should be atmospheric. V squared over 2g, well, we can probably figure that out. That might be one of the things we'd like to know. And then finally, where it impacts the water, which we can think of being impacting a solid surface. It's just easier to think of it that way. Even if actually water is basically a solid surface. If you ever walk across the Golden Gate, it always amazes me that, well, it doesn't surprise you that people commit suicide by jumping off bridges when you walk across the Golden Gate because it's so high. There's a telephone right in the middle of the bridge if you walk across there, which is kind of a sad thing to see, but I guess a sign of reality also. And so you can think of it hitting water just the same as hitting the ground because it has its own inertia and won't move. And so what are the conditions here? Well, the velocity would be 0. The pressure we wouldn't know. And the elevation we would. And so so we have to choose our points between these. So the easiest thing for us to do probably would be to take point 2 and 4. And use those. And let's do that, but let's make life really easy for us by doing something else. Let's take this system. So we're going to think about taking these 2 conditions where we can define behavior. And we're going to shrink our system down to exactly this. We're going to have this tank, which is the weight of the person. And we're going to have the smallest height here between points 2 and points 4, which are this point here and this point here. And we're going to shrink this basically down to 0, so this height of water is nothing. So in other words, it's the amount of force we have to do to get us off the ground in the first place, not to get us 10 meters up or however far up we are. And so then we can write our equations exactly for that. And so we can write Bernoulli. So what's Bernoulli going to look like? It's going to look like Z2 plus the pressure at point 2 divided by the unit weight plus V2 squared over 2g. And it has to be equal to the magnitudes at point 4. Again, pressure, unit weight, plus velocity 1 squared over 2g. We can go back to our what we know panels, but we don't really need to do that because we kind of know what's going on. Well, the reason that we've made this water column small is because all of a sudden we can put Z4 and Z2 the same as each other. And so we don't have to worry about it. Sorry? We do know them, but if we put them infinitely close together, instead of knowing what they are, we can just put them equal to each other and we don't have to deal with it. The equation's just easier. Yes, go ahead.
Why did you use V1?
Because I'm an idiot. Yeah. Thank you. Yeah, great. And it should be P4 as well. So what do we know about these? We know that the pressure at P2 we said is 0. We know that the velocity at V4 is 0. And so coming out of this, we just have V2 squared over 2g is equal to P4 over, I'll write it as rho g. So the reason for getting rid of the z's are just the fact that we don't have to deal with whatever that length is. If we added that length, we could do. If we added that length, we'd also have to think about the weight of that water as well, because we'd like to do a free body diagram for this. So the other thing that we'd like to do is that we can think of this as a pressure acting upwards, which is P4. And so if we do our free body diagram, we have WP acting downwards, and then we have a force acting upwards, which is just equal to the pressure at point 4 multiplied by the cross-sectional area of this jet. Right? So the jet has an area. And so what we could do is we could rewrite this expression. We'd like to be able to figure out, we know what the weight of a person is. So this is going to be 100 kilograms, and we know what that is in terms of the mass of the person is going to be 100 kilograms, so the weight is going to be 1,000 newtons. And so what we'd like to be able to do is figure out this. Well, we also know from this that the weight of the person has to equal the pressure at point 4 multiplied through by, go away, go away. No, it doesn't want to go away. Fine. Lost my train of thought, multiplied by A. And so what we could do in this, we could multiply. So in other words, pressure at 4 times A is going to be equal to this. So what we could do, we're going to multiply both sides by density and gravity. Density and gravity. We're going to multiply both sides by cross-sectional area. And so now the whole term on this side is just this. It's this. So that's our expression that we need. And so we've got our expression exactly the way we want it. We don't know what pressure is, but that's implicit in here. We know the pressure has to be times the area of the jet has to be equal to the weight of a person. And so we can rewrite this expression. I still want to get rid of this. It's bugging me. Finally. So let's rewrite this as that. So what is it? So we have area times density of water times V2 squared over 2 is equal to just WP, weight of a person. And so the term we want to get is V2 squared. So we just rearrange that, and we end up with V2 squared is going to be equal to everything else taken to the other side. The weight of the person multiplied by 2 divided by the area of the jet multiplied by the density of water, and that's it. And so what are these? 100 kilograms times 10 meters per second squared, 9.81, equals 1,000 newtons. Times 2. What's the area? Well, you saw it. I think it's 4 inches. 4 inches by 4 inches. That's just a convenient area. 4 inches is 10 centimeters. So 10 centimeters is 0.1 of a meter. So 0.1 of a meter by 0.1 of a meter. We don't care that's a circle. We're going to put the area as equal to 0.1 meter squared on edge, which is 10 to the minus 1 squared. So this is meters squared. Density is 1,000 kilograms per cubic meter, which is kind of nice because those cancel out. And we just end up with V2 squared is equal to its square root of 10 to the 2. 2 times 10 to the 2. And it would be meters squared per second squared. You can check the dimensions. So V2 is equal to 1.4 times 10 to the 1. Square root 2 times square root 10 to the 2 equals 14 meters per second. And the conversion, I just looked it up on Wiki, is about 2 to 1. So it's about 28 miles per hour. 28 mph. Wow. Sounds reasonable. I don't know what the number should be, but sounds like a reasonable number in terms of what we're looking at. So just by using Bernoulli, making the assumptions, writing our 6 components, we only don't know one of them. The one we don't know is velocity. We take care of the unknown pressure because we make sure that the pressure has to equal the reaction of the weight that we're holding up. And so we can come up with a velocity that we have to apply in this jet to be able to make that work. And so that's interesting, but not completely, because it doesn't really tell us anything about the pump that we have to use to get that. So if what this is physically saying is that we have coming out of this nozzle, basically, something that comes out at 14 meters a second. And that is enough to do what we need to do with this particular case. But what about the amount of power that we need from that? So it's not an obvious shot from this, but take it on trust that we can do that. So what is power? This is, we know that the force coming down from this, well, we know the force must be what? 1,000 newtons. So work is the, power is the rate of doing work. Equals rate of doing work. So work is equal to force times displacement. Rate of doing work is per second. So it's a force times a velocity. So actually in this case, what you can do, it might not be so obvious, but you can take this force that we have to apply. It's kind of moving at some velocity, 14 meters a second, even though it's static. And so we can get the power output would just be equal to 1,000 newtons times 14 meters a second, which is equal to 14 times 10 to the 3 Newton meters per second. Newton meter is a joule. A Newton meter per second is a watt. And so apparently the amount of power we need is of the order of 14 kilowatts. No idea whether that's the right size. I looked up again on Google last night what conversion factor is from watts to horsepower. And so apparently 1 kilowatt is about equal to 1 horsepower. So it's about 14 horsepower. Right order of magnitude, I guess. I'm not really sure exactly what it should be, but it doesn't seem, it's not a crazy number. So what's a powerful car? About 100, well, not very powerful car is about 100 horsepower, right? Which is moving it.
Question, wait, 0.2 and 0.3, would they be equal?
Say it again, sorry?
0.2 and 0.3 be equal?
0.2 and 0.3 I think would not be, yeah, they would be equal if it's shrunk down. It's only equal if it's shrunk down so that column of water is nothing. Because otherwise the column of water has some weight, okay, which you'd have to include in it. That was our main reason for doing it. Yeah, 2 reasons. One is because it makes 2 and 3 equal elevation, and so the we can get rid of the z's. But yeah, the main thing is that we'd have to account for that column of water weight. So that's good question. Okay. All right. So that is that's the basic calculation. So I don't know. So get used to being able to look to see what you don't know and be able to solve for that. But So I don't know if 14 horsepower is the right number. I don't know what these, I guess you could check online to see what they're rated at, but sounds like a reasonable number. The other thing, very quick calculation here. We used this last year and I thought it was kind of interesting. So the land speed record, self-powered land speed record. So this guy's a Scot. He's the guy, I think, who is represented in the movie The Flying Scotsman, if ever you saw that, about a kind of a track racer making bikes out of bits and pieces, doing the Olympics on the cheap. And so here it is, land speed record of 56 miles an hour. So you can do the same calculation. What's the output that you need to be able to get up to that velocity? You have everything you need to be able to do that calculation as well. It's actually quite similar to this, the calculation you just done here. It's probably a two-liner, right? And so there's this guy lying down, pedaling somehow. Velocity ahead of this, hitting its head, and in hitting its head, it builds up a pressure. Call this point 1, call this point 2. What do we have? The elevations are the same, so we don't care about that. We call the pressure at point 1 atmospheric, so we don't care about that. We call the velocity at point 2 0 because it's saltating, stagnating, saltation point, stagnation point, and so we don't worry about that. And so the only components we have left are that the pressure at point 2 divided by the unit weight of air has to be equal to the pressure, the velocity at 1 squared over 2g. If we want to know what the force is that's applied, again, it's actually exactly the same expression, isn't it? The force is equal to P2 times an area. And so if we multiply both things by an area, and we multiply both sides by unit weight, then this is written in terms of the force. And if we just put some numbers in that to figure out what this force is, then what is it? This guy's land speed record was 60 miles an hour. Is there a budgie in here? A budgerigar? We said you can do the conversion. It's about 30 meters a second. It's a factor of 2. So it's 30 meters per second squared. The area, I don't know, 1 by 1. I've done the calculation already, so 1 by 1 is too big, but let's use it anyway. This is in meters squared per second squared for this one here, right? And unit weight of air, which is rho g, which would be it's 10 newtons per meter cubed, roughly, for air. So it's 1 kilogram per meter squared multiplied by 10 meters per second squared. So it's 10 newtons per 10 newtons per cubic meter over 2g, and g is 10 meters per second squared. So if you do the math on this, what's it come out at? We get rid of 10, we get rid of 10, we get rid of 1, we have a half. So the force is equal to a half times 30 squared. So 3 30s are 100, 30 30s are 1,000-ish. So this is 10 to the 3. And it should be in newtons. I haven't been very careful with my units. Let's see if that's right. Yeah, so it's about 500 newtons. Order of 500 newtons. We can do the same calculation as before, that power is equal to velocity times force, right? This is meters per second. This is newtons, so it's newtons, meters per second. So this is work. This is rate of doing work. And so if we're going at 30 meters a second, multiplied by 500 newtons. It's equal to 15,000 Newton meters per second. Newton meter is a joule, and a joule per second is a watt. 2 T's. And so it's 15 kilonewtons, which is the same as 15 horsepower. So you're getting 15 horses worth of effort out of this guy. I don't think we're 15 times as strong as horses, so I think the calculation's a bit off. Apparently, if you look it up, I'll just go off this, I'll come back to it in a second. If you look up what human power is, power of a cyclist is something of the order of half a kilowatt, 500 watts. So not right. So you have to look at what we've done not so right. And I would guess if I was to look at something that we didn't do so right, is it scales directly with the size of this frontal area. You know that when you go through, want to go fast, you duck down and try and make yourself as small a frontal profile as possible. A meter by meter is pretty big, right? It's same. Well, it's bigger than this, right? So this is a meter across here, so it'd be this big. That's probably 2 meters, right? So it's probably this 3 feet by 3 feet. So the frontal area is probably off, and it's probably not killing the velocity right at the front. And so you probably have to reduce this by a factor of 100. 100 would get you to 0.15, so 150 watts, which is about it. So we're using, this is too big by a factor of 100 probably, I would guess. And it's not accounting for the fact that it's streamlined. He's not pushing a 1 meter by 1 meter slab in front of him. He's got this kind of fancy bicycle that he is ergonomically lying down on, and it's moving ahead at some relatively small frontal area. And I guess that's his butt, isn't it? I guess that's his face down here. And it's streamlined. It's got this trailing edge here to stop eddies forming and sucking you back in terms of being aerodynamically efficient. So those are useful calculations to be able to do. So they all come out of our idea that we can use Bernoulli's equation to be able to define, hopefully, out of behavior along a streamline, 6 components, be able to know 5 out of 6 of them so you can solve for the remaining ones. That's not always the case. So sometimes we only have 4 variables that are known, and we need to constrain our system in some way. And so one way we can do that is by using the principle of conservation of mass or volume. And so the only idea is that if, for instance, we only knew 4 of our variables, and since we're writing things along a stream tube, we could, instead of thinking as a streamline rather, which is typically how we've written things, a streamline could be this surface along the top here, between 2 points, 2 and 1. It could also be this point here along the bottom, between 2 and 1. And it could also be this intermediate one. But the bottom and top portions of this actually define a stream tube. And it's clear that in this stream tube, since it's steady state, taking a snapshot, the velocities aren't changing. The volumetric flow rate, the velocity at location 1 times A1, has to actually equal the velocity at location 2 times A2. These have to be equivalent to each other. So what this observation does is if we look at stream tubes and how things look upstream and downstream, we can actually allow ourselves to not know 2 of the components in our equation because we can constrain one of them by just setting the upstream velocity. This would allow us to scale. So this would allow us to say that the velocity at point 1 times A1 is equal to the velocity at 2 times A2. And so it also allows us to say that the velocity at 1 is equal to the velocity at 2 multiplied by just the ratios of those 2 areas, which we hopefully know. And so if we know what the areas are, we know that the velocity is a point downstream. We can intrinsically link that to the velocity upstream, or vice versa. And so using continuity or conservation of mass or conservation of volume, it's called a variety of different things. Using this principle, we can actually get away with knowing only 4 of the components as we write things along a streamline and solving for the others. Okay? And so I'm not sure whether we have to use that in... Okay? So that's another principle that we will need. So remember this. So remember Bernoulli, and remember this expression as well, because it allows us to provide extra constraint. In the few minutes available, let's just talk about free jets. This principle kind of applies to free jets in some respects. In the simplest way when we deal with it, what we can assume is if we look at a bucket with a hole in it, depending on the assumptions that we want to make, yeah, we have enough time to do this. So we could think of this as, for instance, a big bucket or a small bucket. So if it was a small bucket, that would mean that the surface area at the top was relatively small. And as a function of that, we'd have to say something about being able to constrain the velocities at this point. So if the bucket is small and water's flowing out of it, and as the cross-sectional area of the top of the bucket gets closer to the cross-sectional area of the bottom, then no longer will the bucket level remain constant as a function of time. It will drop down. So it violates our principle of Bernoulli, which is a steady state condition. If we think of it as a very big bucket, code in these questions, a big bucket, a big reservoir, that's code for saying that the water level of this doesn't draw down with time, and that the velocity at this point is pretty close to 0. So if this is big, then the velocity here we can set as equal to 0, which makes life easier. And if we wanted to calculate the rate of flow out of this bucket, then we can just write behavior along this streamline, where we write conditions at this point. What will they be? Velocity is 0, atmospheric pressure, elevation. We know this, right? C1. Likewise, where it just comes out of here, we know that the velocity 2 is not 0. We know that for the same arguments about pressure at point 2, it comes out into the atmosphere. Atmosphere is acting on its side, so presumably at all points it's the same. So this is 0. And we also have the elevation at 2, which we know. And so out of this, the only things that we don't know are this expression here. And so we can write Bernoulli in terms of that, and I won't go through it. You can work it out for yourself. Basically, well, not basically. Well, it's written here. So what do we get rid of? Pressure 1 is 0. Pressure 2 is 0. We know the elevations at these 2 points, so we can write the difference in those elevations. And we're just going to write Z1 minus Z2 is equal to H. And so we have that. That's a quarter 2. That's my alarm going off. We know that this is 0. And so the only terms we have to worry about are this. And that's it. Right. We have this and the elevation change. And so not surprisingly, we end up with the equation of a free jet, which is this. We solve for V2. And if we solve for V2, what do we get? We get V2 squared is equal to unit weight of water times H over times 2 over rho. Gamma is equal to rho g. And so this is GH2. And so the equation of a free jet, not surprisingly, is the velocity 2 is equal to square root 2gh. Standard result that was on our sheet as we started off today. And so it basically says that the higher the level in the tank, not surprisingly, the faster the water comes out of the bottom. It's not a linear relationship, it's a square root relationship. I suppose you could write this as square root 2g, which is a constant, multiplied by square root h. So as you double the height of the tank, the water velocity only increases by square root of 2, 1.4 times. If you quadruple the height of the tank, it'll come out double the speed, square root 2. And so we can use that to calculate the velocity comes out of the tank. We could also, if we wanted to, calculate if this thing keeps on coming down, a bit like the jet lev, right? But it's a column of water which is just being powered by the weight of fluid in the tank, not pressurized at the surface. And we could use that to write Bernoulli, say, between 0.2, and I won't do it, but if we write Bernoulli between this expression here, where we now know the velocity, and we write it here, where we'd like to find out the velocity, what are the conditions? Pressure here will be 0. The velocity here won't be velocity 2, but be velocity 5. And we know the elevation of this, which is a different elevation. And if we go through that, we'll end up being able to calculate that at this lower point. I won't do the calculation. The velocity as it comes out further down is just equal to the sum, the sum of the two heights. So the total height from the water surface to the bottom of this jet, it comes out of the bucket here at velocity 2, and this velocity 2 is square root 2gh in terms of this height. It comes out of the bottom of this jet at a velocity which is much larger and equal to the whole distance between these things. And it's given by that. And so what, as the other interesting thing that we could surmise about that, which is one of the reasons that we took our jet lev condition to be simpler. Well, the one is that you see from this is that clearly V5 is greater than V2. Not surprising. It's actually the same as if the water comes out and it's going at this velocity and it accelerates just like dropping something down. So it's no different from dropping something onto the ground. It's the same as a weight that's traveling downwards. It just happens to be liquid. But the velocity it's going at would be exactly the same as if you used your statics and dynamics equations to figure out what the velocity was of a weight that you dropped from the height of the top of the tank. By the time it gets to 0.5, it'll be going at the same acceleration just by dropping it. But the interesting thing, I think, which relates to this, is that we also know that the velocity 5 times the cross-sectional area at 5 has to equal the velocity at 2 times the cross-sectional area at 2. And so if we think about this in terms of our jet lev jet, or indeed this jet, this area 2, since the velocity at 5 has to be greater than the velocity at 2, we know that the jet has to be coning. And if you look very carefully at a tap, a faucet that's running, you see it comes out of the faucet at some width, and as it goes down in free fall, it'll get slightly narrower. And it gets narrower according to this basic relationship. And so a couple of the reasons that we didn't do the jet lev with this big column of water is if you make the column of water small, you avoid two problems. You don't have to factor in the weight of that water when you're doing your free body to calculate the pressure that's acting up on the bottom. And you also don't have to account for the fact that the areas change as you go down through the jet, as you go down through the system. And that's, I think that's all we want to, that's all we need to talk about. And so those are the things we started off with today. I guess we got through them. They're kind of summarized here. The equation of a free jet, relatively straightforward, scales with square root 2gh. And the fact that if we only know 4 of our parameters in the Bernoulli equation, and we really want to solve something, we can write continuity, and that takes care of one of the parameters. Okay? Perfect timing. Questions?